At the dawn of the 20th century, mathematics appeared to be on the verge of achieving a long-held dream, an age of absolute certainty. The magnificent edifice of 19th century analysis, built upon the foundations of set theory, seemed to offer a complete and consistent universe of truth. This serene confidence was shattered by a single, devastatingly simple discovery. In 1901, Bertrand Russell uncovered a contradiction lurking within the very heart of the new logic, a paradox that threatened to bring the entire structure of formal reasoning crashing down. The intellectual crisis was profound. It directly targeted the life's work of Gottlob Frege, whose monumental Grundsätze der Arithmetik represented the most advanced attempt to ground all of arithmetic in pure logic. Russell's paradox, concerning the set of all sets that fail to contain themselves, revealed a fatal flaw in Frege's system, turning the quest for certainty into a desperate salvage operation. From the rubble of this collapse rose one of the most ambitious intellectual monuments ever constructed: Alfred North, Whitehead and Bertrand Russell's Principia Mathematica. The Principia was a direct and heroic response to this foundational emergency. Its grand objective was the logicist thesis, the demonstration that all mathematical truths could be derived from a select group of self-evident logical axioms and a few rules of inference. To achieve this, Russell and Whitehead synthesized and radically extended the work of their immediate predecessors. From Frege, they inherited the very ambition of the logicist project, seeking to repair his flawed system. From the Italian mathematician Giuseppe Peano and his Formulario Mathematico, they adopted and refined a powerful symbolic notation, creating a language precise enough to express complex mathematical ideas without ambiguity. Their primary challenge, however, was to tame the wild, beautiful, and perilous concepts of Georg Cantor's transfinite set theory, the very domain where the paradoxes had spawned. They needed a system that preserved Cantor's insights while preventing the logical self-reference that led to contradiction. The core of their solution, the Principia's central and most intricate piece of machinery, was the ramified theory of types. This theory imposed a strict hierarchical structure upon the universe of discourse. At the lowest level, type 0, exist individuals, the fundamental objects of discussion. At the next level, type 1, are classes whose members are exclusively individuals of type 0. Ascending further, type 2 contains classes whose members are exclusively classes of type 1, and so on, ad infinitum. The governing principle is absolute class, where a proposition about a class must always be of a higher type than its members or subjects. This elegant stratification renders the original paradox impossible. A set is forbidden from being a member of itself because its members must be of a strictly lower type. The question of whether the set of all sets failing to contain themselves contains itself becomes syntactically meaningless, a mere ill-formed expression. The hierarchy was further complicated by a system of orders within each type, a technical refinement designed to thwart subtler paradoxes arising from what were called impredicative definitions, where an object is defined by reference to a totality to which it itself belongs, a deep concern raised by the influential Henry Poincaré. While the theory of types successfully prevented paradoxes, it created a new and severe problem. The rigid hierarchy was so restrictive that it rendered significant portions of classical mathematics, such as the proof for the existence of the least upper bound of a set of real numbers, unwieldy or impossible to derive. The logical fortress they had built was secure, yet it locked out many of the treasures it was designed to protect. To remedy this, Russell and Whitehead introduced a powerful and deeply controversial tool, the Axiom of Reducibility. This axiom was a brute force postulate, asserting that for any propositional function of a high and complex order, there always exists a logically equivalent, coextensive function of the lowest possible order, a first-order function. This effectively collapsed the intricate hierarchy of orders when needed, restoring the power of classical analysis. Its inclusion, however, came at a steep price. It was an ad hoc device, a patch lacking the intuitive, self-evident quality of a pure logical truth. Russell himself would later lament its inclusion, famously describing it as a blemish upon the work's aesthetic and logical purity. The colossal scale of the Principia's logical apparatus is perhaps best appreciated through its treatment of the most elementary arithmetic truths. The work culminates, after hundreds of pages of dense symbolic deduction, in proposition star 54.43 of the second volume, the proof that 1 + 1 = 2. This is the apotheosis of the logicist method. Here, the number 1 is defined as the class of all classes containing a single member. The number 2 is defined as the class of all classes containing 2 members. The operation of addition itself is a complex logical construction upon these classes. The proof, therefore, becomes a laborious demonstration that the logical union of any class from the class of singletons with another distinct one yields a class belonging to the class of pairs. This monumental effort to derive a truth known to every child reveals the true scope of their ambition to leave nothing to intuition, to secure every last brick of the mathematical edifice upon the unshakable bedrock of pure, formal logic, the titanic effort of Principia Mathematica is best appreciated through its treatment of the most elementary arithmetic truths. The work culminates, after hundreds of pages of dense symbolic deduction, in proposition star 54.43 of the second volume, the proof that 1 + 1 = 2. This is the apotheosis of the logicist method. Here, the number 1 is defined as the class of all classes containing a single member. The number 2 is defined as the class of all classes containing 2 members. The operation of addition itself is a complex logical construction upon these classes. The proof, therefore, becomes a laborious demonstration that the logical union of any class from the class of singletons with another distinct one yields a class belonging to the class of pairs. This monumental effort to derive a truth known to every child reveals the true scope of their ambition to leave nothing to intuition. Yet, while Russell and Whitehead were completing their colossus, a young logician in Vienna was preparing the very intellectual dynamite that would shatter its foundations. In 1931, Kurt Gödel published his paper on formally undecidable propositions. His two incompleteness theorems delivered a fatal blow to the entire logicist enterprise. The first theorem established that any formal system powerful enough to express basic arithmetic, a system like the one in Principia, would contain statements that are true but remain impossible to prove within the system itself. The dream of completeness was an illusion. The second theorem compounded the devastation, demonstrating that such a system could never prove its own consistency. The very certainty Principia was built to guarantee was, by its own logical structure, unattainable. The great fortress of reason contained a fundamental, irreparable breach. The collapse of the logicist dream did little to diminish the work's philosophical resonance. Instead, it became a powerful catalyst for new lines of inquiry that defined 20th century thought. Ludwig Wittgenstein, Russell's own brilliant and mercurial student, took the logical framework of Principia to its ultimate conclusion in his Tractatus Logico-Philosophicus. He treated Principia's formal language as a map of reality itself, exploring the boundaries of what could be said meaningfully. For Wittgenstein, the logical scaffolding of the world mirrored the logical scaffolding of language, and the limits of one were the limits of the other. His work was a profound meditation on the silence that lies beyond the reach of a perfect logical calculus. Concurrently, the Vienna Circle, a group of philosophers and scientists, including the influential Rudolf Carnap, seized upon Principia's technical apparatus for their own radical project. They wielded its formal logic as a scalpel to excise metaphysics from meaningful discourse. For these logical positivists, a statement held meaning only if it was either analytically true, like a tautology in Principia, or empirically verifiable. They saw in the austere symbolism of Russell and Whitehead the ideal tool for constructing a purified language of science, free from the ambiguities of traditional philosophy. Principia became their standard, their methodological Bible, even as its original purpose lay in Rue. Paradoxically, the most enduring practical legacy of Principia Mathematica emerged from the very aspect that made it so unwieldy, its radical formalism. The project's insistence on reducing all mathematical reasoning to a finite set of axioms and mechanical rules for symbol manipulation laid the conceptual groundwork for an entirely new field. Alan Turing, a figure whose intellect would shape the modern world, directly engaged with the questions of provability and decidability that Principia had placed at the centre of mathematics. His groundbreaking 1936 paper on computable numbers introduced the abstract concept of a Turing machine, a theoretical device capable of simulating any algorithm's logic. This was a direct response to the Entscheidungsproblem, or decision problem, which asked if an algorithm existed that could determine the truth or falsity of any mathematical statement within a formal system. By proving that a general algorithm for the decision problem was impossible, Turing not only echoed Gödel's limits on formalism, but also, in the process, invented the universal model of computation that underpins every digital computer today. The methodical, step-by-step process of a Principia proof became the abstract blueprint for machine execution. This transformation of a theoretical constraint into a practical foundation is most striking in the evolution of Principia's theory of types. Initially conceived as a complex, ad hoc solution to prevent the self-referential paradoxes that had undone Frege's work, the theory organized mathematical objects into a strict hierarchy, where a set could only contain elements from a lower level. Within the context of pure logic, it was cumbersome and restrictive. Decades later, however, this very concept found a spectacular new application in the nascent field of computer science. It evolved into the type theory that forms the backbone of modern, statically typed programming languages such as ML and Haskell. In this new domain, a type system serves as a powerful tool for preventing errors before a program ever runs. It enforces a logical consistency on the data a program manipulates, Catching whole classes of bugs at the compilation stage, the hierarchical structure designed to save logic from contradiction was repurposed to create more robust, verifiable, and secure software. A philosophical safeguard became an engineering principle of immense practical value. In the final accounting, Principia Mathematica stands as one of intellectual history's most magnificent and fruitful failures. It remains a vast, unread mausoleum dedicated to the dream of absolute logical certainty, a 3-volume testament to an ambition that turned out to be impossible. Its central quest to ground all of mathematics in a provably complete and consistent logical system was definitively thwarted, yet the work's true significance lies in the spectacular nature of its collapse. It was a heroic siege on the citadel of truth, and the debris from its shattered walls provided the building materials for the next century of thought. The rigor it demanded and the formal language it perfected became indispensable tools for philosophy. The questions it posed about the limits of mechanical reasoning gave birth to the theory of computation. The intricate internal structures it devised to avoid paradox found a second life at the heart of software engineering. Principia Mathematica thus occupies a unique dual role. It is the definitive monument to the search for certainty, a grand project whose failure revealed a more profound and complex landscape of mathematical reality. Its ruins became the unlikely, yet essential, foundation for our modern understanding of formal systems, the limits of reason, and the digital architecture of the world we now inhabit.